Hello everyone and welcome back. In this video we're going to introduce a few more hypothesis tests. Now first of all, these are not my tests and it's not pronounced the same way. These are called the chi-square tests and there are three different types. They can be used to determine whether the distribution of a single categorical variable fits a model distribution. They can be used to determine whether the distribution of a single categorical variable is the same across different groups, or they can be used to determine whether there's an association between two categorical variables. So the first test that we will look at is called a test of goodness of fit. As the name suggests, this type of test is used when we want to see whether the distribution of counts in a single categorical variable will fit a predicted model. So let's take a look at the assumptions and conditions that are required to perform the test. Now the first condition is called the counted data condition, which says that the values in the table must be in counts. So these values cannot be relative frequencies or percentages or numerical data. Then we have the usual independence and sample size assumptions. We check the independence by the randomization condition, and we can check the sample size assumption by the expected cell frequency condition, which says that the expected counts for every cell in the table must be at least 5. To obtain the expected counts for a goodness of fit test, we take the predicted proportions by the model and then multiply them by the sample size. Now the test statistic is called the chi-squared statistic and is found by taking the sum of the squared differences from the observed and the expected counts divided by the expected counts. Now the test statistic is denoted by what looks like an x squared, where the symbol x is actually the Greek letter chi. Now the sampling distribution models that we need to use for these chi-square tests are called the chi-square distributions. Now the chi-square distributions are right-skewed distributions which depend on a parameter called the number of degrees of freedom. And the examples of the chi-square distributions are shown to the left for degrees of freedom 3, 4, and 5. Now to calculate the degrees of freedom for a goodness of fit test, we take the number of categories in our categorical variable and subtract 1. Now the chi-square test statistic is only used for hypothesis testing, and they are not used for constructing confidence intervals. Now if the observed counts do not match closely to the expected counts, then the test statistic will be large. And if the test statistic is small, then that means our model will fit the data well. And so if the test statistic is large enough, then we can reject the null hypothesis. So once we find the test statistic and the sampling distribution model, we will then use that model to determine an estimate for the p-value. So we refer to table X for the area under the chi-squared distributions. Now this table will provide the right tail probabilities at the top of the columns. Now the best that we can do without using technology is to provide an interval of values of where the p-value may lie. So to find the interval containing the p-value using table X, we first find the row that corresponds to the degrees of freedom along the first column. Then we read across to find where our test statistic falls under. Then the p-value will fall between the right tail probabilities of those corresponding values. So let's take a look at some examples of using the table to find the probabilities under the chi-square distributions. So let's find an interval estimate for the area to the right of a chi-squared value of 10 with 3 degrees of freedom. So what we're looking for under the chi-squared distribution is the area to the right of 10. So the first thing we'll do is locate the number of degrees of freedom along the first column. So here we have 3 degrees of freedom, and now we want to read across the row to see where the value of 10 falls within the table. So the value of 10 falls between 9.348 and 11.345. And along the top row is the right tail probabilities. So let's write down what these probabilities are telling us in the table. So the table is telling us that the area to the right of 9.348 has a right tail probability of 0.025. So mathematically, we're given that the area to the right of 9.348 is 0.025. Now let's also write down what the other value is telling us in our table. So to the right of 11.345, the right tail probability is 0.010. So the area to the right of 11.345 is 0.01. So mathematically, we're given that the area to the right of 11.345 is 0.010. So if we know that the area to the right of 11.345 is 0.01, and the area to the right of 9.348 is 0.025, then how much area to the right of 10 will it have? Well, from our values that are given in the table, what we can say is that the area to the right of 10 is between these two areas. So it will be between 0.01 and 0.025. And using math notation, we can write this as the area to the right of 10 is some value between 0.01 and 0.025. And this is the best we can do in estimating the area using the table. So the area to the right of 10 is smaller than 0.025, but larger than 0.01. So now let's look at the next example. Let's find an estimate for the area to the right of 54.09 with 11 degrees of freedom. So we'll first locate 11 degrees of freedom in the table, and now we need to determine where the value of 54.09 will fall within this row. So if you look at all of the values along the row, 54.09 is to the right of the table. So it is larger than 31.264. So it's somewhere on the right of the table. So now let's write down what the closest values in the table is telling us. So the table tells us that the area to the right of 31.264 is equal to 0.001. So mathematically, the area to the right of 31.264 is equal to 0.001. And so what we want is to determine the area to the right of 54.09, which will correspond to this area. So if the area to the right of 31.264 is equal to 0.001, then that tells us that the area to the right of 54.09 has to be smaller than 0.001. And so mathematically, we can write this as the area to the right of 54.09 is somewhere between 0 and 0.001. So the best that we can do using our table is to say that the area will be less than 0.001. So now let's look at the next example. Let's find an estimate for the area to the right of 20 with 15 degrees of freedom. So the first thing we'll do is locate 15 degrees of freedom in our table, and then we want to find where 20 falls within that row. So if you look across this row, we see that 20 falls to the left of the table. So it is smaller than 22.307, so it falls somewhere to the left of the table. So let's write down what the probability is telling us for the closest value. So the table says that the area to the right of 22.307 is equal to 0.1. So under the chi-square distribution with 15 degrees of freedom, this right tail area is 0.00. And what we want to find is the area to the right of 20. So we know that the area to the right of 22.307 is equal to 0.1. Then that tells us that the area to the right of 20 is larger than 0.1. And so mathematically, we can write this as an interval. So the area to the right of 20 is some value that is between 0.1 and 1. And again, this is the best that we can do when we use this table. So let's take a look at another example. Let's find the area to the right of 90 with 75 degrees of freedom. So the first thing we'll do is look for 75 degrees of freedom along the first column. Now notice that there are no values for 75 degrees of freedom. The table jumps from 70 to 80 degrees, and so the rule is to round down to the closest degrees of freedom if it's not listed in the table. In this case, the closest degrees of freedom to 75, that is in our table, is 70. So now we'll look for where the test statistic of 90 falls between, and it falls between 85.527 and 90.531. So let's write down what the table gives us for those values. So the table tells us that the area to the right of 85.527 has a right tail probability of 0.1, and the area to the right of 90.531 is 0.05. So now let's draw what these areas look like under the chi-square distribution. So the area to the right of 85.527 is equal to 0.1, and the area to the right of 90.531 is equal to 0.05. And what we want to look for is the area to the right of 90. And so this tells us that the area to the right of 90 will be larger than 0.05, but smaller than 0.1. So it will be between 0.05 and 0.1. Now the mechanics of a chi-square test will work like a one-sided hypothesis test. However, the interpretation of a chi-square test is many-sided. Because there are more than two proportions, there are many different ways that the null hypothesis can be false. Since we're squaring the differences, we make the deviations positive, whether the observed counts are higher or lower than the expected counts. So there's no direction when we reject the null hypothesis. All that we can conclude is that the data does not fit the model. So let's take a look at some examples of a chi-squared goodness of fit test. So let's suppose a company that fills grass seed bags wants to evaluate their machine. So the following distribution is as advertised on their bags. So we're given 5 different seeds with the proportions of each seed. Now the company wants to check if the seed distribution in the bags fits the advertised distribution. So they took a random sample of 1,000 seeds and then counted each seed type. So we're given the observed counts in this table. So let's carry out a test of hypothesis with a 5% significance level to see whether the advertising label is giving a true description of the contents of the seed bag. Since we're given a model distribution and we're looking to see whether the data that we have fits this certain model, then we're going to perform a chi-squared test of goodness of fit. So let's first determine the expected counts for each of the seeds. Now to find the expected counts, we take the sample size and multiply it by the predicted proportions from our model. So the expected counts for seed 1 is 1,000 times 0.5, which is 500. The expected counts for seed 2 is 1,000 times 0.25, which is 250. For seed 3, we have 1,000 times 0.15, which is 150. And for seeds 4 and 5, we have 1,000 times 0.05, which gives us 50. So now let's write down the hypotheses for the test. For the null hypothesis, we assume that the proportions of each seed is equal to the modeled proportions. So in this case, the proportion for seed 1, we assume that it's equal to 0.5. The proportions for seed 2 is equal to 0.25. The proportions for seed 3 is 0.15. And the proportions for seeds 4 and seeds 5 are equal to 0.05. Now the alternative hypothesis is that at least one of the proportions differs from the advertised proportions. So now we'll check the assumptions and conditions. So the first assumption, or condition rather, is the counted data condition. So the data that we have must be in counts, in which they are, so this condition is satisfied. And then we have the independence and sample size assumption. And so one type of seed should not affect the other types of seeds. So to check for independence, we look for randomization. We're given that we have a random sample of 1,000 seeds, and so this condition is met. And then we have the sample size assumption. So we need a large enough sample. And we'll check the expected cell frequency condition. So all of the expected counts must be greater than 5. And since we calculated all of the expected counts, we know that they are all larger than 5. And so the expected cell frequency condition is met. So now we can calculate our test statistic. So we have a chi-squared statistic where we take the sum of the observed counts minus the expected counts squared divided by the expected counts. So for the first type of seed, we have an observed count of 480 and we expect 500. So we take 480 minus 500 squared and we divide it by the expected, which is 500, and then we add this to the same calculation but for seed 2. So we have 233 observed minus 250 expected squared over 250. And then we do the same calculation for seed 3. We observed 160 and expect 150. And then for seed 4, we observed 62 and expect 50. And lastly, for seed 5, we observed 64 and expect 50. And so if you were to perform the calculation, we end up with a chi-squared statistic of 9.923, rounding to 3 decimal places. Now we also need to determine which sampling distribution model to use to find the p-value. So we need to determine the degrees of freedom, which is the number of categories minus 1. So here we have 5 different types of seeds, so that there are 5 different categories, and so the degrees of freedom is 5 minus 1, which is equal to 4. So the p-value is going to be the area to the right of 9.923 So we want to find an estimate for the area to the right of 9.923 with 4 degrees of freedom. So using our table, we first locate 4 degrees of freedom, and now we want to determine where the test statistic of 9.923 will fall within that row. So we see that 9.923 falls between 9.488 and 11.143. So let's write down the corresponding areas that are given to us from our table. The table tells us that the area to the right of 9.488 is equal to 0.050, and the area to the right of 11.143 is equal to 0.025. And so this will tell us that the p-value, which is the area to the right of 9.923, will be between 0.025 and 0.050. So now that we have our p-value, we can compare this to our significance level. So the alpha level is 5%, and we found that the p-value is between 0.025 and 0.05. So since the p-value is smaller than alpha, which is 0.05, then we reject the null hypothesis. So since we rejected the null hypothesis, then this means that there's sufficient evidence to conclude that at least one of the proportions differs from the advertised proportions. And so the data that we have does not fit the model well. And so this tells us that they may need to reevaluate their machine. So let's take a look at another example. Suppose we have a bag of candies with 6 different colors, and it advertises the following proportions given to us in our table. So you randomly choose a bag and count the number of candies. Carry out a hypothesis test with a 5% significance level to test whether the color distribution of candies is as advertised. So let's first find the expected counts for each of these candies. So to find the expected counts, we take the sample size, which is 167, and then multiply it by the predicted proportions. So for the brown candies, we will take 0.3 and multiply it by 167, which gives us 50.1. Then for the red candies, we take 0.2 and multiply it by 167, which gives us 33.4. The same is for the yellow candies, so 33.4. For the orange, green, and blue candies, we have 0.1 times 167, which is 16.7. Now let's write down the hypotheses for the test. So for the null hypothesis, we assume that the proportions for each of the colors are equal to the modeled proportions. So the proportion of brown candies will be equal to 0.3. The proportion of red candies will be equal to 0.2. The same is for yellow candies. And then the proportions for orange is 0.1. The proportion of green candy is 0.1. And the proportion of blue candies is 0.1. And the alternative is that at least one of the proportions differs from the advertised proportions. So next, let's check the assumptions and conditions. So we have counted data. So the counted data condition is met. And we need the independence assumption. So this means that the color of one candy should not affect the color of other candies. So here we check the randomization condition, and we have a random sample, so this condition is met. And lastly, we check the sample size assumption. So we need a large enough sample. And we check the sample size assumption with the expected cell frequency condition. So all of the expected counts are greater than 5. And so this condition is met. So now we can calculate our test statistic. So the chi-squared statistic is the sum of the observed counts minus the expected squared divided by the expected counts. So for the brown candies, we have observed 50 and expect 50.1. So we square that and divide it by the expected, which is 50.1. And then for the red candies, we have 32 observed, then we subtract 33.4 expected squared over the expected, which is 33.4. And we do the same calculations for all of the different colors. So we have 30 minus 33.4 squared over 33.4 plus 18 minus 16.7 squared over 16.7 plus 22 minus 16.7 squared over 16.7 plus 15 minus 16.7 squared over 16.7. So if you perform this calculation, our test statistic is 2.361, rounding to 3 decimal places. So we also need to determine the sampling distribution model. So to find the degrees of freedom, it is the number of categories minus 1. So here we have 6 different categories, so 6 different colors, and so the degrees of freedom is 5. So the p-value is the area to the right of 2.361 with 5 degrees of freedom. So we want to find an estimate for the area to the right of 2.361. So if we look in our table under 5 degrees of freedom, the test statistic of 2.361 falls to the left of the table. So the closest value is 9.236. So let's write down what the table gives us for the area. So the table tells us that the area to the right of 9.236 is equal to 0.1. So the area to the right of 9.236 is equal to 0.1. And so this tells us that the p-value, which is the area to the right of 2.361, is going to be larger than 0.1. And so the p-value is going to be in between 0.1 and 1. So now let's compare our p-value to the significance level. Our significance level is 0.05, and observe that our p-value, which is between 0.1 and 1, is larger than the significance level. And since our p-value is larger than the significance level, we fail to reject the null hypothesis. Since we failed to reject the null hypothesis, this means that there is insufficient evidence to conclude that at least one of the proportion differs from the advertised claim. And so this tells us that the model that we have for the distribution of candies, our data will fit the model quite well. So that concludes our lesson for this video. In the next video, we will look at the other two chi-square tests, and I'll see you then.